Attendees are in listen-only mode.
Hello, good afternoon, good evening, dear participants. It's a pleasure to welcome you today with active interest in becoming part of fast-growing power quality solutions to improve performance of Indian utilities. APQI, or the Asia Power Quality Initiative, is an independent platform that aims to build awareness and capacities on issues related to power quality. This initiative has local chapters in as many as 7 Asian and Southeast Asian countries. The APQI is currently in its 5th year. This pan-Asian platform, supported by national support network partners, continues to carry out activities towards capacity building and awareness raising amongst various stakeholders. We further work to facilitate regulatory and standards initiative in respective countries. We provide a neutral platform for exchange of knowledge and best practices concerning power quality. Our website www.apqi.org, supported by Leonardo Energy Europe, is the single largest resource for discussion papers, research and data on power quality in all the countries we work. We work with a focus on shared learning, transparent exchange of information and active engagement in the field. I welcome you all on behalf of APQI India to this maiden webinar, Business Case for Power Quality Investments by Indian Power Distribution Utilities. As you are knowing, loss reduction, one of the foremost business performance metrics that drives the overall viability of a distribution utility. The problem gets aggravated when the two loss components, technical and commercial, are treated independently. Technical losses as CAPEX intensive and commercial losses as OPEX intensive. One binding theme that brings these two areas together is power quality, and that establishes a strong interrelation across the supply chain. Our two industry experts from ABB and Crompton Greaves Limited will explore and discuss potential techno-economical PQ solutions for the distribution utilities for a long-term benefit, covering various technological advancements on PQ equipment and its management in conventional and non-conventional grid today. Mr. Pannalal Biswas, Assistant Vice President from ABB, has over 21 years experience. He heads the complete range of PQ products in the company. Dr. Samsul Ekram, Assistant General Manager at Global Research and Development Centers from CGL, has over 20+ years experience. He has over 23 papers published and presented, awarded 1 Indian patent, and filed 19 more in the area of power quality. I sincerely hope you will experience a good discussion during today's session and look forward to your active participation in future too. Thank you.
Good afternoon and Good evening to all the participants and to APQI and the panelists. I am Pannalal Viswas from ABB. I would like to take through the presentation regarding the power quality investment by Indian power distribution utilities. The basic presentation which I am going to cover in this is the key element of major power quality issues. What is the poor power quality in distribution network? Type of compensator presently used in most of the distribution utilities. Advantages and disadvantages of different types of power compensator, and how to arrive a better techno-economical power quality solution for the distribution utilities for long-term benefit, both user point of view as well as the end user. The key elements for the power quality issues are mainly three. First is the reactive power compensation. Second is load balancing. As you know, most of the demand today also is going for the power quality in terms of improving the, reducing the unbalanced load, so that neutral current can be reduced and neutral to earth potential can be minimized. Next is talk about the harmonics. These are the three main issues as far as the power quality issues are concerned. So as I explained, content, key elements, power quality, what are the poor power quality in the distribution network, type of compensator, technical advancement in the power quality field, and advantage, disadvantage of the power quality compensator, and techno-economical solution, which will be beneficial both for the utilities as well as for the end user. And major issues, as I explained, is basically because of the three issues, which is mainly related to the field of reactive power, then load unbalance, and the harmonics. And this is which is causing the high running cost or failure of equipment and resultant customer dissatisfaction. So if you look in this major key issues which is causing from the reactive power improper management, is causing the poor power factor. As you know, most of you, the power factor is nothing but the useful power to the total power ratio. So if reactive power is not managed properly, it also causes under voltage and over voltage variation, as the rate of change of voltage or delta change V is nothing but in proportional to the reactive power variation, and it depends on the short circuit level. So higher the short circuit level, you can see the lower will be the voltage fluctuation. System losses, which increases due to both inductive as well as capacitive power, and deficient harmonic compensation, overheating of power equipment, or failure of control equipment, and unwanted trippings. And unbalance, which I said, enhancing the life of the power equipment, reduces the overload on the individual cable and over additional losses. Now when you talk about the other issues which is mostly seen in the most of the utilities with voltage flicker, sometimes it is also coming out from the reactive power change, voltage dip. Sometimes it is also seen as the wide range of frequency variation, failure of frequent failure of OLTC which is used in the transformer in order to control the voltage because of the frequent movement. Sometimes it also causes problem. HTLP ratio at the system losses and technical losses. If we look into the distribution utilities today, it is in the range of 7 to 10%. When you talk about HB to 33 kV or 11 kV system, it is about 1.5% or 1.6%, and medium voltage to low voltage it is in the range of 2%, and below low voltage is in the range of 4 to 6%. So this is obvious that we need to put the compensation at distribution system as well in order to minimize the technical losses. Equipment failure, maloperation is also one of the reasons of poor power quality, and equipment overheating and damages of transformer, OLTC, PCs or UPS, and more electronics introduction is there into this distribution network, digital relays. Those things are also getting affected because of the power quality issues. In terms, if we think about why it is required to improve the power quality. So broadly, if we see, there are basically 4 issues. One is increasing the load capacity. That is because these will provide additional capacity to the distribution system. Thereby, we will be able to connect more loads and increase the revenue. Technical savings, there's the loss reduction as I explained, which is in the range of 7 to 10% in most of the distribution system. Extended electrical plant life, which is reduce the electrical burden on cables, switchgear, etc. And environmental benefit ultimately, like the reduce of power consumption, means the less greenhouse gases emission. Now, conventional way of distribution utilities, when we talk about the power quality, they means only capacitor, which is nothing but either it will be a fixed capacitor, or like you have a 11 kV system or you have a 33 kV system, there will be some 2 MVR or 5 MVR or 7 MVR depending on the substation rating. They go for a fixed compensation with reactor, without reactor. Sometimes they also introduce the switch capacitor bank. It may be in the steps of 1000 KVAr or 1500 KVAr, but both resulting into if you see fixed compensation, then always it will provide a constant reactive power. But if you look at the nature of the load, it keeps on changing depending on the time to time. So it cannot provide the required compensation which is necessarily demanded by the distribution network. Then if you look at the switched capacitor, again that also minimizes, but it produces a lot of transients. So every time I switch on one capacitor, then it also produces a lot of transients. It takes 100 to 200 times of its rated current. So that causes also disturbance in the network, and sometimes it also causes the electronics component failure. So even though these also cannot make a smooth compensation. When we go for the next technology, that is basically nothing but we call it as stepless compensation. Now, stepless compensation, which is nothing but a IGBT based or inverter, voltage source converter, which is mostly used to generate the inductive power or capacitive power or unbalanced compensation. as well as harmonics to some extent when there is necessary for the harmonics compensation. Next, we are talking about the power quality compensator, which is basically a stepless compensation and can provide both inductive as well as capacitive power. And the response time, which is very crucial here, which is basically IGBT based converter. You can see which it can generate both capacitive as well as inductive, and this is a very fast and dynamic response. The smooth and stepless compensation, it can be fraction of KVAr or fraction of unbalanced compensation. It can generate both inductive as well as capacitive reactive power, unbalanced compensation, and operation in shunt with the load. We can see here the response time when we talk about from inductive power to capacitive power. It takes just about less than a cycle. Similarly, when it takes from capacitive load to inductive load, that is also it is taking less than a cycle response time. So which means that its reaction is very instantaneous, with step change, very fast dynamic response, excellent steady state transient. Even during the changes, you can see the current response is sinusoidal nature. We can see it can work both in closed loop as well as open loop, and 4 cascade control loops in wheel. And this system can work both. You can see here the load current, which is consisting of active current, reactive current, and negative sequence, which is causing the unbalance. What active compensator does basically, it subtracts the complete reactive power as well as the negative sequence. So thereby, after subtraction this reactive power and negative sequence, the balanced active current is only drawing from the distribution transformer. So it has got 3 directions. It can go 0 to 100% capacity, or it can go 0 to 100% inductive, and it also can go 0 to 100% unbalanced compensation. Here is a example, few cases. You have a transformer. There are different types of loads current here. There is one phase where the current is 0, first phase. The Y and P is full loaded. But if we put the active compensator here, it draws this kind of current. So when we add these 2 current, then we find the total current which is coming from the grid is basically balanced current in all 3 phases and without any reactive power. Now, if you have different kinds of other applications where there can be 200 amps R phase and 180 amps Y phase, and 300 amps B phase, and these phases also. This is the type of compensator current which is generated, anti-current, and this can be also compensated by means of this active compensator. So you can see all 3 cases that whatever be the nature of the load here, whether it's a 2-phase or whether it's a unbalanced, inductive or unbalanced, capacitive, in all 3 conditions, the incoming current which is coming from the grid is always it is a same balanced and active power only. Typical presentation which shows about a active compensator, which, as I explained, it can generate both inductive capacitive power, instantaneous support response for the fluctuating distribution load, and unbalanced load compensation, and suitable for both low voltage, medium voltage, and can be used also to step down transformer. It is a modular design. As you see, it can, if the number of panels can be increased depending on the required load, and they all can be connected through canvas. So wide applications, it's going for high-speed train attraction application. It is used for the power distribution network. It can be used for blast furnace, steel industries, wherever welding loads, automobile industries, and etc. Key benefit is that your objective on this is the improve power quality, enhance reliability to the end user, enhances the energy efficiency by reducing system losses, reduced carbon footprint, and reduce the maintenance need and enhance the life of electrical installation. And finally, improve the reliability of the existing capacitor bank, which under dynamic condition was not able to meet the desired requirement. And no risk of resonance or harmonic amplification, because this is an active-based compensator, so it is not consisting of inductor capacitor solution, which is a passive. Next, we are is the advantages and disadvantages of different types of power quality compensator. First, we will talk about the fixed or switched capacitor bank. We will talk about the SVC, which is nothing but a thyristerized either switched capacitor bank or thyristor controlled reactor, and the STATCOM. So this is the type of compensator, basically a fixed. Here it is thyristor switched. Here also it is thyristor switched along with the filter bank. And this is a completely different, that it doesn't have any capacitor. It's a voltage source converter basically. And in terms of losses, if we compare, then we will say that here the losses will be less. The switched also it is no load condition is less. TCR where the losses will be higher because you will need both reactor as well as capacitor combination. Actually, fixed capacitor is the one, or filter bank is the one which gives the variable capacitive power fixed. But because of the reactor, by changing the firing angle of the reactor, you will be able to draw variable inductive power. So both fixed capacitor minus variable inductive power is causing the variable capacitive power. And we have all the devices, switching losses and converter losses. Here power quality rating, it comes as a Q. Where also capacitive power is required Q and inductive power is Q. And if you see the voltage source converter, it works in both directions. This is also Q rating. For the same rating, here the range is 0 to Q, here it will be 0. Terms of response, if the capacitor, the response is very slow because it takes time to discharge the capacitor before you energize the reconnect the capacitor. In case of switching devices which is used in SVC, it is used mostly thyristor, and the STATCOM it is also affects the device. Here it is also IGBT or IGCT used. Harmonic is generated, inbuilt filter is adopted. This is how it is a DC capacitor, and you have a voltage source converter with the PWM reactor which can produce inductive power as well as capacitive power. So in terms of the reactive power range, it can give from -Q to +Q. Next, we can see that as it can give from minus to plus both range. If we have most of the electricity utilities, they are already having some fixed compensation, as I explained. Conventionally, they use that fixed switch capacitor. So if we combine it along with this, the StatCom, then you can look here. Once it is combined, then it goes from plus 100 to minus 100. So it means it is from 0 to 200, and the capacitor can never have to be switched on and off. Without that, it can keep directly from 0 to 200%. So just by adding on one solution into the existing system, it can be upgraded to a variable to 0 to 200%. Here is an example how the unbalance is affecting the network. Suppose you have a two-phase load, and if the straight losses is 2 times I square R system losses. If this load is divided into 3 phases, the same current will fall by I by root 3. So losses will be 3 times I by root 3 square into R. So which means I root 3 and 3 will get cancelled. So it becomes I square R. We make it in balanced system, then the losses is drastically reduced in the system, and thereby upstream also distribution and transmission line. Here one pictorial view about how this power quality is affecting to the user. You can see normally we need basically the green active power, but because of the nature of the load, it is combination of both active as well as reactive. So red reactive power is also started coming, and recently because of the power electronics introduction in the drives, UPS and so many other loads, converter and all, we also produces the harmonics. So outside the transformer doesn't look like it is having so much of pollution in terms of electrical network. When we measure the harmonics analysis as a system study, we found that these transformers are not only loaded to not only designed for the active power supply, but also it has to take care for the reactive power, it has to take care about the unbalance, it has to take care about the harmonics, etc. So now if we look that if we design a filter bank which is already existing in most of the utilities, so that can absorb the harmonics, as well as it also can provide some amount of compensation, maybe let's say 1000 KVAr, but still we need additional 1000 KVAr. So that additional reactive power and unbalance current is still flowing from the transformer, so that we can compensate by means of advanced solution, advanced IGBT solution, which is very fast and instantaneously can kill the either capacitive power, inductive power, or the harmonics, and also the unbalance. This is one financial data which was published in European Copper Institute in 2002. We can see one incident, per incident the losses in terms of the semiconductor industry, it is about 3.8 million euro. Financial trade, it is also about 6 million euro. Computer center, it is 7.5 lakhs euro. Telecommunication, about 30,000. Steel industry, 3.5 lakhs. So sometimes if it's a data center or some semiconductor industries and all, the losses are enormous. If we do not consider this power quality also as a part of the initiative in this. And as Mr. Manoj rightly pointed out, the APQI has taken this initiative. It is not only the technical losses which we are talking about, it's technical plus the commercial. When we talk about the commercial, how much losses are happening for per incident for the industries or for your consumer. If we can take care, we find that if we claim a few percent extra for energy bill, nobody will be claiming any kinds of issues out of it. But it is most important to get a reliable and deliver a reliable power supply. Like today in scenario Delhi, because the last 15 days almost there is no power. But this is because we are not taking care all kinds of power quality initiative which is required for the distribution network in earlier days. Here is another example about the small scale industries, which is about 3,000, and large transformer losses in terms of about 10,000, low LV cable, additional motor losses due to the additional voltage. So these are the other effects, which is affecting the power quality very broadly. Here is a typical installation photograph that we can have a filter reactor, as I said, which can be taken care for the part of the existing capacitor bank or the filter bank or the fixed compensation, and balance dynamic. We can add this module depending on the voltage level and ratio. So we can put the active compensator, which will take care for the rest of the compensator, which will take care for the rest of the power quality requirement. It is a typical 110 kV by 33 kV installation. You can see, let's say it is a 10 ampere station where we can have some amount of 1500 kVAr filter bank, and we can put plus minus 1500 kVAr STATCOM. So which in turn it can give a total solution of 0 to 3000 kVAr. This is calculated considering that in MBA contract demand is 0.8 power factor and 80% loading on the transformer. So the average kV is coming around 8000. If we recommend to go for 0.99 power factor, the total compensation required for this is about 3000 kVAr, out of which improved power factor we get about 6869, that is 6869 as against 8000. So we get a reduction in KVA is about 1131. As I said that this power, wastage of power is nothing but the generating of power, if we can save it. So if we calculate this even for a 16 hours two shift basis, I just estimated the cost is coming, which we can save additional revenue which can utility can get from other consumer is in the effect of something about 26 million. Considering 16 hours per day, 24 days in a month and 12 months per year at the rate of 4 rupees per kVA, like AP and UP and all these estates. It is something around 6 rupees and all. I am taking a conservative figure, but still it is coming around 26 million. If we take a MB solution, it is about, let's say, 1.4 million, and a GBT based system, even if it's 13.3 million, all put together close to around 15 million. So we get a ROI less than a year. So this becoming very attractive. In the process, we are also safeguarding all our equipment. In the process, utilities are able to serve more customers by improving the power quality, which earlier they were not able to give them support because there was no kind of compensator which we can reduce the consumption and reduce the draw of current, which is not as per the power quality requirement. So this definitely, certainly we have to look into this, that how we can jointly work and how we can improve the utilities in our grid and network. Here are few installations like in various applications it goes. So in conclusion, problem which is day to day we are facing, or increasing the availability of the power consumption. Make it fixed and switched capacitor. Alone neither cannot provide the instantaneous stepless reactive power compensation as well as the distribution load requirement. Today, IGBT based instantaneous active compensator along with fixed compensation or filter bank can be a perfect solution for the improving power quality and increasing the more customer base by providing the, because of the energy saving, we are able to give the support to our other consumer as well, and in the installation more for the environmental friendly. With this, my presentation. I'll close it here. In case if you have any questions, please raise it. Thank you, all the participants.
This is Ikram from Compensator. Thanks to my colleague Panal Vishwas for a good highlights on the power quality. Basically for end consumer, whatever he talks, that how it will be useful for the end consumer, what will be the return on that, and what are the different products for the end consumers are there. I will basically try to cover up the utility part. As you know that as a CG we are more towards the utility, and we will what we are doing as a part of the utilities, and how different products are helping towards the utility. That part I will try to cover up. In whole, my presentation will organized as a power quality for distribution utilities. What all the problems are there, what can be the solutions, how to get the solutions, that also I'll try to cover up a bit of, and the effect of the bad power quality. I think Pannalal has covered up most of that, equipments and all sorts of things, but what will be the effects on that, how a system or that equipment or the product will get affected for that, and power quality product solutions for distribution utilities. That's mostly cover up for that control, management of a conventional grid and management of a non-conventional grid, and a new think or talk is going on towards that peak power control or the peak power management. And in case of the control, both the passive and the reactive, including all the KVAr and online tap changers and fault current limiter and all sorts of are there. In case of the management in conventional, all of we know about the smart grid, and in non-conventional the new thing is going on, that is the microgrid and hybrid grid, and these new concepts of thing is going on there. I'll try to cover up certain thing on that, and the focus will be towards that this T&D losses and all that. That anyhow I'll conclude at the end of my slide. And I'll put one business cases also, but as I will cover, or I will try to talk about that power qualities for the utility as a whole. So example for the business cases will be very big, and which I'll not be able to cover, but there are a couple of publications on various plant and various system, and what will be the impact of the power quality and that ROI for that if I buy a power quality equipment and install it, and what will be the return of investment of that. There are a couple of papers of that I have not added here, but I'll try to explain certain thing on that about that, how to calculate and how to arrive the impact of that. So coming to my first slides, that is the basic needs of the power qualities for the utilities. As Mr. Pannalal just discussed that Delhi there was no power for the last 15 days. I have first question, I'm not asking any answer for anyone, but the question is that do we have less electricity? Answer on you, but I will say that in India today, if you look any distribution franchises or discoms, they will claim that they have a 20 to 30% T&D loss. If you put the Korea as a small country, they have 4.01% T&D loss today. They have a mission to make all metro cities by 2020 in smart grid, and by 2030 complete Korea will be under the smart grid. And they claims that by the time our T&D loss will be exactly nothing, negligible or something like that. Compare the 4% versus 20 to 30%. It means indirectly 20 to 30% of our power is going in a wastage condition. Is it due to the inefficient load? Still we are using 100 watt bulbs and all sorts of things. No one is tuned about these LEDs and all that. Still we are using a 70 watt fan and that type of loads. No one is tuned about 30-35 watts lamps and all sorts of things. Is it that we have a less or the smart intelligence load control and the monitoring? Still we are in manned intensive type of, less of unmanned and also sort of thing. And some of our street light, if you look, it works 24 hours continuous or 48 hours also, whether it's day, whether it's night, no one bother for that. Is it we have a less non-conventional, like India, if you look, we have a huge desert and big amount of that offshore, and what is the utilization of that? And last not but the least, do have a bad power quality. Basically, I will talk about the bad power quality, and are we complying as per their IEEE's or all their applicable standards or no. To talk about, Pannala has tried to cover here quickly just about that problems due to the power qualities, like all the nonlinear loads, specifically the variable frequency drives and all that. And all these power quality damages are mandate for today's developed work. I cannot work without these 10 power quality problem creating devices or the equipment or the instruments. So all these are mandate for my today. But I know that they are creating a garbage to my system, and hence the questions comes about the power quality improvement and upliftment of that. Most of we know that this power quality is spikes, sag, outage, and the surge, and basic part is the surge. And a couple of reports are there. It varies from the country to country, but as a whole average we can say that surge is a major concern, and sag and all that parallelly supports the surge and creates all the problem in the system. Who all are the sources of that? All the office equipment, as I discussed a few slides before, and Pannala also talked on that. Lighting, you know that 15% of any country load is that lighting load. So lighting is there another one. All the utilities and neighbors, whatever their industries and all that are there. Effect of the bad power quality. That's the theme of that. Is it the voltage disturbance? Is it excessive current to the neutral? Already Pannala will talk on that. Overheating of the motor. All that controls problems will be there. Unexpected computer crashing. Live reduction of that sensitive important equipment, shutdown or the trips of the system, equipment damage, reactive behavior of sophisticated processed equipment and the instrument, random lockup of the data error and all sorts of things, and the power system overheating and all this are there. I think this is one important one. Those who are hardcore about this real use of the variable frequency drives and know that impact of the harmonics to the real load, and they know that due to this more amount of the harmonic, and if you follow or look towards this NEMA MG1 part 30.1.2.1, this harmonic voltage factor and the impact of that. So it means my distribution utilities, if they are giving a high TSD supply to me, that have an indirect impact to my load. And I have experimentations that each 1% of added harmonics creates 0.35 to 0.37 added temperature rise of critical devices like motor or the generator. So that's the one thing. And another one is the unbalancing. If my system is unbalanced, that creates impacts to my source, that creates impacts to my load both. And as per NEMA, all of we know that there are a de-rating to the system, and I have to de-rate the system, and unnecessarily I have to put the high cost, high value or higher rating system on my that overall one. The power quality solutions, the Pannala has given a equipment along with that, that what are the devices and all that are there. If I summarize that with respect to the classes of LV, MV and HV, these also are that problems like the flicker, interrupts, power oscillation, sag and soil, voltage instability, harmonics, unbalanced load, and the reactive powers and all are there. And if you look at respective solution with respect to these problems, Then if the LV, where the panel has covered most of the part of that, it's basically either the Q support or the TSD or the DVR or some excitation of a generator, mostly, or the oscillation and all that. Active and harmonic filter, both the active and the passive one. Negative sequencing, there's the neutral current and all that. Unbalancing, and StatCom and whatever are there for that low voltage one. To talk anything about the medium voltage, where is our concern about that power quality for utilities and all, that comes more towards that Q support, less I will say TSG, but nowadays due to all these problems and all this intense non-linear load, TSD is increasing, and that is getting reflected as per the transformer ratio to 11 kV, 33 kV and onwards, and that has a big impact on that. And SVC and thyristor control and capacitor and reactor, where we call APFCs and all that are there. And if it be that high voltage or extra high voltage, basically it is SVC. Lot of solution on that SVGs are there, where this static power generation up to certain kV level are also available and popular today. To talk more detail about the power quality specific for this DISCOMs or the distribution utilities, the power that for the utilities it is more of that active and the passive, and the more questions comes here, that whether it should be active or whether it should be passive or whether it should be hybrid, and which will be the cost effective one. As Pannalal tries to put one of his slide, that will it be the fixed capacitor, will it be a variable capacitor, will it be the mix of that, and how I can optimize the cost and create the best outcome of my system by adding both the active and the passive one or the hybrid one and the ratio of one to another one, and make a best outcome of my system creates that all the problems elimination. And that comes towards that SVC with the help of thyristor control capacitor or the reactor for the conventional, reactor for the air core, that is a new field and getting popular due to its robustness and all that, or SVG, load balancing, unbalancing, Pannalal tries to cover up certain thing on that, or that AVR or the all-line tap changing and peak power control, that is the latest and the new need for all that utilities. This basic is known to most of, and as Pannalal said that it's a robust, reliable, and it's more on that positive and negative power management. It's a fact, and it's whether it is for conventional or whether it is for non-conventional reactor like air core and all that, that's the popularity is going on due to its robustness and the reliability towards the system. This is one important field for the utilities, and this is the important instrument for the utilities to improve the power quality of the system and to bring the power factor towards unity and play with that I part, that is that elimination of the reactive one, that is nothing but more intense towards that active one, and hence I am reducing the effective I am reducing the IR drop, I am reducing the T and D losses which we normally claims today. So if I improve the power factor, I am reducing the TSD. That's that one message for utilities from my side from this slide. All of you know that at APFC, active power factor corrections, instead of a conventional, can I have a automated and the smooth one where I can vary in an active way, and where I can put it in a 11 kV poles or in a control panel, and based on the need or based on the problem, I can put wherever is the problematic area one. It means instead of putting to that incoming side, can I put it to the outgoing side, so that my load side is getting mitigated, indirectly impact to the short side or the purchase side is getting managed or met. That's the theme of the slides, and it's a fully automated and a smooth one for both the positive and negative VAR management or VAR compensation. This is one of the important aspects, and without the balancing both the source side and the load side, there is a huge impact in the both the grid and also towards that consumer through the load. And if there is a unbalance towards the load, I have to derate unnecessary to my system, creating a impact of my added cost and impact on my added loss to my system. So can I have a balance towards both the source side and the load side? And it's a automated smooth balancing towards both the system and sides will be there. And you can observe that if it be the unbalance, how it will be, and if it be the balance, how it will be, and if it be the balance, what is the impact. One of my slide I just presents on that. And in load side, as per NEMA MG1, what will be the impact and the derating, that also I just try to cover in one of my earlier slides. Another problem in case of utilities are that fault current limit. And that creates the impact to the power quality indirectly. A frequent fault, frequent surge, frequent dip, frequent interrupt, and overall impacts to the stability of the system or continuous supply to the system, and stability to the grids and all sorts of things. Couple of techniques are there, non-conventional fault current limiter and the conventional fault current limiter and the non-conventional specifics toward the superconducting one in view of resistive and in view of inductive. And if it be the resistive one, which is more popular today, mostly for that series, and added people by a shunt reactor here, and by putting the shunt reactor, people normally tries to enhance the capacity of fault current limiter and try to manage or meet that fault current for the utilities. And if it be the high voltage or high power case, people try to prefer inductive type like a transformer and try to manage it by exciting this coil and manage that fault current, whatever the problems are there. Peak power control, this is one important thing, and basically in India we face a problem of the peak power. It comes in specific time, and can we manage the peak power in that specific time by means of present added techniques of the storage and back to the source and all that are there. And a smooth transaction and monitoring and measure and observe and add to the source based on the load as soon as the peak power is going on, as a automated and smooth control of the peak load and manage it in a remote way or unmanned way as on when it is coming. Smart grid is known to most of us, but in India we are in a booming stage, and unmanned substation and unmanned monitoring control of a substation for the utilities are an important area today. Microgrid is another important upcoming area today, and more than the microgrid, I will cover that hybrid grid also. And as all of you know that non-conventional sources and getting added and creating lot of impact, instead of increasing the transmission, can I have a localized generation and get integrated there, and instead of transmitting and creating a more T and D losses, if I have a localized one, indirectly I am saving or I am reducing the transmission and distribution losses on my system. So it is more in case of the distribution, in case of the storage, in case of the load, and in case of the generation. And will it be islanding type or non-islanding type as per IEEE 1547? How that integration will happen and how I can get a better microgrid system as per my need and the requirement, and where I am putting that one as a view of hybrid power system. That's an important area today, and that helps lots towards that T&D losses of my system, and that gives a localized power improvement in view of unbalancing or in view of my peak power control, and all that will get managed and mitigate. And a hybrid power system is an important area for the utilities today. Is it a hybrid grid? Is a new area. people are started talking about the blackout and brownout and all sorts of things are there. Can I have, if you look today in India, most of the cities, as Pannala also highlighted, that Delhi there was a 15 days no power and all that are there. In India, most of the small cities, people are more and more familiar about this UPS and storage and all sorts of things. Look, the efficiency of one storage system and getting the power from the grid, storing and feedback or to the load and all sorts of things. Overall efficiency of the system. Why I should reduce the efficiency of my generated power just by storage and de-storage and putting to the load? Can I have a hybrid system? Can I have a blackout and brownout concept? Can I give a important customer, instead of UPS, a temporary DC source with respect to that a minimum amount of the load, like a minimum need and the requirement, so that he is not going motivated towards that storage and creating that efficiencies of my high cost generated power and dumping in a storage and back to that grid once again. And last not by least about this unmanned is the today's popularity about the digital. Can I move instead of analog one towards the digital one as a more efficient monitoring, control, management, leading towards the less transmission and distribution losses? Can I have a more efficient with a less copper? Today, if I have an analog, all the signals are coming via the copper one. If it be a fiber optics one, all the coppers is getting eliminated. And I have a better and better control. I have a better and better in field level monitoring, and that is getting reflected towards that control room. And overall system, as per the need and requirement, I can monitor, I can control, and I can manage my system more efficiently and robustly. And that's the concept of this digital is coming instead of a conventional one as an analog one with a lot of copper wiring, higher cost, and lot of probabilities of the failure of the system with a less redundancy, I will say. This is the concept of digital substation. I'll not go more deep on that, but basically it is like that. I'll cover, I have 5 more minutes, so I'll cover by the time. But basically it is a substation with more towards that level 0 or the primary equipment or the process level intelligence, and same is getting reflected to the protections and control level and the station's control area. And here the focus is more in this domain. Can I have a conventional or non-conventional equipment? Can all the equipment be intelligent and getting monitored and controlled so that the interruption, so that the life is getting estimated, so that the fault is getting predicted and system is working in healthy in 24/7 and 365 days without source of problem in case of my system. There are a couple of things about that digital substation, whether it should be the conventional or the non-conventional one, and all that applicable all that plus points of that are there, like a cost reduction, improved safety, standardizations and interconnectivity, reliability, asset optimizations, that is that life and all that will come, investment optimizations, and communications capability improvement, and all that will come in that case. There are a couple of techniques or standards are available there for automation and smart grid. Most of is available, and most of are followed while people are trying to do towards the digital substations and towards that unmanned substations and all. Coming to this cost analysis of utilities, as I told that it's a big part, but in short, it is load flow improvement, power factor improvement, Pannala tries to cover up of that, TSD improvement, Pannala has covered up of that. I will try to cover the surge, spike, deep, and the fault level improvement and all that. Unmanned monitoring control, less transmission and distribution losses, which is the most pending area for us today, and less outage of the trip, which will give a 24/7 supply to my system. basic calculations. Maybe all of you can use this one as a tools of the calculation, and based on these tools you can create your mathematical formula and implement to the system. And if you add this to the system, you will come to know that how the payback and return of investment of any power quality system is getting added. This is the problem, and to solve the problem, this is the cost of my problem recovery. So instead of creating the problem and getting that loss due to the problem, if I have a power quality, I am eliminating the problem, and that goes to my return of investment of my system. And that comes as a total cost of the power distribution, which is more towards that employees involvement, that my system is shut down, then what that added resources including human and machines and all are required to make the system healthy. The restart time of that, effects of my productions, and certain hidden cost is also involved on that, in view of that my system life will go down due to the frequent surge and impulse and all sorts of things, and how that is getting impacted to my cost of the system, and as a overall the total cost of the power distribution we can calculate based on this, and based on this we can estimate the return of investment whatever the power quality equipment I am going to install to my system. At the last of my slides, what should be the way forward? Rather, how an organization like we are going to improve the total power quality and for the utilities. And if I give an example of one of our system where we have implemented, before the implementation we had a T&D loss something above 30%, 30 to 35%. Today we have 19%. End of the year we have a plan to make it 50%, and next year we have a target to make it 12% as a T&D loss. And more than that, this Q improvement which Pannalal tries to cover, and that harmonic improvement which gives a unnecessary fifth harmonic, second harmonic, which creates nothing to the system, because all that torque and all sorts of thing is depends on the fundamental one. So how I can eliminate that unnecessary harmonics except the fundamental, and how also I can reduce the Q part, make more P and reduce the I, and create the impacts on my IR losses of the system. And here I will just try to put the three part, one as a load flow improvement, more distributed generation instead of a concentric one, more ring connections of the feeder instead of a star and all that, so that localized it can get managed as per the load is coming, more active power factor controller for the better voltage profile, for the surge, dip and the fault current improvement. Can I use that DVR or the Q support? Can I add the fault current limiter so that my abnormal fault and all that sort of things should not come? And if I have to make a less T&D losses, better power factor, that is controlling the I, less TSD, that is dependence only the fundamental, less usage, more uses of the more armored cables, so that hooking and all that in India we have that problem, I can reduce. More towards that hybrid type of supply or LVDC type of supply with a blackout and the brownout concept. So these also really creates a impacts towards that load flow improvements, towards the less surge, spikes, dip and that fault, and also the transmission and the distribution losses. I think that's all from my side. Thank you very much to all for your kind attention. Over to the organizer. Thank you.
Participants, we heard Mr. Bishwas from ABB and Dr. Ekram from CGL. Now is the time to bring up the questions which our expert speakers would be replying. I have one question which is that in most of the residential applications there is plenty of single phase loads, and those single phase loads like office equipments, they cause a lot of unbalance, and in turn this causes unbalance across system. End users often complain that it is very difficult to balance single phase loads at their end. What are the different solutions available for balancing loads? I would request Mr. Biswas to reply this.
Okay. Thank you, Mr. Manoj. See, there are
Can you hear?
is below the transformer. Why the transformer? Hello? Are you able to hear? The question I asked him that why there is a blower below the transformer, under the transformer. The operator told that it is basically cooling the neutral. Otherwise, the neutral is getting heated up so much because it can take 2.5 times the rated current of the line. So this is the kind of damages which is happening. And if you see over a period of years, as my earlier presentation, Dr. has covered, because of the recent more and more, sophisticated or more and more power electronics, nonlinear loads are getting added to our domestic application. So this is also producing lots of harmonics, and these harmonics finally resulted into the line. So if we do not compensate at the time of the low voltage side or maybe medium voltage side, then oftenly they will go upstream and they will create more problem, and more havoc problem can happen like how it has happened in other states and countries. So there are devices available. As I said, there is a STATCOM based system or active filter based system which is available in today's market in various parts, and various organizations are supplying that. So this can be used for connecting in the transformer output, which will bring down the balancing all the loads as well as bring down the neutral current, and thereby neutral to earth voltage. Because another experience which I say that one of the network service provider, BSNL, inside the processor actually, if you see, they work at a very low voltage, 1.3 volts. And the neutral to earth voltage, because of the unbalance, it reached more than 5 volts. And there was a damages that happened, and the server got tripped. And they had to pay for just 5 minutes down on the server, they had to pay some 10.5 crores. So that's the kind of, because the server was down, Yahoo was down, and they had to pay huge penalty for that. So they were asking, do we have any solution for that in similar kind of application? So it is very much, it's available today, and there are so many companies that are also providing this kind of solution.
Right. Thank you, Mr. Biswas. We have a second question. What percentage of 20 to 30% T&D loss could be coming from poor power quality? I would request Dr. Ekram to address this question, please.
Look, the power quality is equipment which manage the I and V part. So if I have a system where I have a good V, that is the voltage profile, Vt equals to Vm sine of omega t. And if I have a good I, that is It equals to Im sine of omega t without such a big plus minus phi, then my problem is get solved and I can reduce the I need to my load. So if I have a if I have to improve the TND, I should have a 2M. One is that can I make I without Q, that is less I, because there is a less Q, and can I have a only I1 instead of I3, I5, I7, I9, I13 and I11 and all sorts are there, which is not contributing to my torque or layer performance of any motors and all that equipments are there. Rather, they are killing the life of my equipment due to the high frequencies. So basically, if I have to improve the percentage of TND loss by means of power quality, I have to improve the Q, that is less Q, and I have to improve the TSD, that is the less TSD. And by this, a good percentage of TND loss can be reduced. And as I told, from 30 plus, today we are nearby 20, we have done nothing more than adding this power quality. Now we are planning to add unmanned and all sorts of things, and some theft and all that, where we are planning to bring 15% and further at 12%. So it gives a good amount of savings.
Thank you, Dr.
Thank
Ikram.
you.
The next question we have, what would be the best solution for high voltage harmonics 10 to 15% in LV side? I will repeat the question. If you have a high voltage harmonics to the tune of 10 to 15% on LV side, what will be the best solution? Mr. Vishwas, please.
Yes, this is basically whether LV side voltage harmonics, obviously current harmonics will be more predominant. The reason, as Doctor has explained regarding the fault level of the system is going down. So lower the fault level, that means the distortion will be very high, fluctuation and voltage also will be high, and flicker and all this stuff. So what we can do, actually one way is doing that passive filter, and it used to be done. But with passive filter, sometimes because of the increasing load, because passive filter is designed one time. So you can carry out the study, you know what is the fundamental current, what is the peak 7, 11, 13. You can design the perfect reactor and capacitor voltage, and you can design a passive filter. But what reality happens actually, after 2 years, there will be some more load will get added in the network, there will be some more harmonics will get added into the network, additional requirement will come. So all these things over a period of time, if you see after installation, within 2 years the filter doesn't work. So another solution is that we can go for active compensator, like active filter or this kind of IGBT system, which is basically independent of your system fault level. So because this is a voltage source converter, we can just connect the voltage source converter and keep the CCTV feedback from the high voltage side or low voltage side, and then it can operate by selecting the particular harmonics. Because the moment we connect to the filter will tell before switching on that what are the harmonics available in the network and what is their order. Whether fifth harmonics is 200 ampere, seventh harmonics is 70 ampere, or ninth harmonics is some other magnitude. So we can, there is a possibility that there are many active filters are in the field in the market, where you can select the particular harmonics which will bring down the harmonics distortion within the IEEE 519 or G5/4. Even there are selection that you want to make it as per IEEE 519. If you select that kind of things, the algorithm is already fit into the program. So which is select particular harmonics which is required to get compensated in order to bring down the voltage less than 5% TSDI or TSDB.
Well, thank you, Mr. Vishwas. We have another question. This is of course very interesting from a common man's perspective. As a general user of electricity, how I am protected from the damages occurring due to sudden overvoltages to my domestic equipments, TV, refrigerator, lights, etc. I request Dr. Ekram to respond to this.
Look, basically all the DISCOMs or the utilities, we try to maintain the voltage at a certain level. Fortunately or unfortunately in India, most of utilities fail to do that, and there is no norms, rules or regulations for that, due to that it is coming and creating the problem. Stabilizers and all that is not the solution to the issues and all sorts of things. Couple of things are there and getting implemented in India as that non-conventional sources are getting popular. It is already implemented in Europe, and I have one case where I have already implemented by means of AVR come OLTC, online tap changing. And if you look the old concept of online tap changing, that was a conventional mechanical type of, and recently we have a solid state, that is a power electronics based tap changing, where you can make a smooth voltage control and all that. Basically what happens for this case that during daytime, while there is a non-conventional sources like solar is getting added, then automatic system voltage goes up, and this AVRs and OLTCs plays a bigger role to manage that. India, unfortunately, is a popular one. We have implemented in a couple of places, but most of the rural part and all that places, there is a less voltage, hence nothing are there. But yes, equipment to say is AVRs or the OLTC that can protect and make a smooth. Yeah.
But from domestic customers' point of view, what measure he can adopt to avoid this kind of voltage surges?
Look, except stabilizing in his or her end, if that utilities are giving something bad, as a user, either like I'm getting a dirty water, so I'm putting a filter. So no other options are there.
Thank you. The last question we'll take. We have a number of other questions as well, but this last question is a little interesting. And I request all the participants that will share the coordinates of our experts later on, and also will outreach through the website. So if you are having already put the questions and not getting the answer right now, we will definitely address this on later through the website. So the fifth question which we have is the Indian government making it compulsory to make use of LED lighting for high efficiency? Dr. Ekram, if you have any information, otherwise I will supplement.
As per my information, answer is no. I don't know how much government participants are there, but badly to say that we talk less, we talk more, do less. We make a lot of things like we should have efficient loads and all sorts of things. How many of fan today or lights today are going in the market, which is a really energy efficient? Still we are using bulbs and CFL and all that. How many of our motors is I4 grades motors? Still we are using I2 motors. Still we are making a local made motors, and all sorts of things are there. So all that problems are there, but as per me, there is nothing. Government norms or regulations are there that LEDs have to be compulsory. Yeah, Manasa, you can add. You can add. Yeah.
I think the LED is becoming more and more popular, and with the time, it is the market which is going to drive it. There is nothing statutory which is going to come from Indian government, as far as our knowledge goes, that LED would be made compulsory in near future. And of course, the country can become energy efficient, but not power quality deficient in a lighter vein. So with that, we are closing this particular webinar, which was the first webinar on APQI platform. I take this opportunity to thank you all the participants from India, Thailand, Malaysia, Philippines, Oman. I also thank our expert speakers, Dr. Ikram and Mr. Pannalal Vishwas for making it possible. I hope that you all have had an enjoyable session. I thank P Manifold and my colleagues to make it a successful thing. And with this, we close this webinar for today. We look forward to meet you again, and please be in touch and adopt a high power quality approach. Thank you. Good night.
Thanks.
Thank you very much.
Thanks.
Bye-bye.